Hello and welcome to Tonight at 8 from the RSGB. Ever since the 2017 Solar Eclipse QSO Party, Ham Radio Science Citizen Investigation, or HamSCI, has been bringing together amateur radio operators and professional space scientists to develop new and innovative ways to study space weather and its impacts on the ionosphere and radio propagation. Tonight we're going to find out more, both from Nathaniel Frissell, W2NAF from the University of Scranton in Pennsylvania, who leads the HamSCI project, and Gwyn G3ZIL, who is on the RSGB Propagation Studies Committee, who will explain why he enjoys the HamSCI experience so much. So welcome to both of you to Tonight at 8. Nathaniel, can you give us a quick overview of what you'll be covering this evening?
Sure, David. Thank you for having me. So today's talk is called HamSCI, Space Weather We Can Do Together. I'm going to talk about some of the results from our very recent Festivals of Eclipse Ionospheric Science and talk a little bit about what HamSCI is going to be doing in the future and how you can get involved.
Excellent, we can't wait. But if you're at home watching this on Monday, the 12th of May, then this is live. And you can ask questions or make comments on either YouTube chat or BATC messaging at any time during the presentation or straight afterwards. Please include your first name and call sign if you have one within every message. And note that you can make this video stream fill your screen on most devices, usually by double clicking on the picture or pressing the full screen button. So now let's go back to Nathaniel and Gwyn to find out more about HamSCI.
Thanks so much, David. I appreciate it. So yes, HamSCI, Space Weather We Can Do Together. So a little bit about me and how I got involved in this. So I was first licensed when I was in middle school in 1998. My original call sign was KC2DXJ. And that introduction to amateur radio there led me to an entire career in academia and education. When I was in grad school at Virginia Tech in 2015, I started HamSCI, got my PhD from Virginia Tech in 2016 in the SuperDarn research group. And we do have some SuperDarn partners in the UK, particularly with the British Antarctic Survey. In 2019, I began as a faculty member at the University of Scranton. I just got tenure this year, and I've spent time researching and doing ham radio operating in a number of remote places around the world, including Svalbard, down in McMurdo Station, and on Adak Island in the Aleutians. So HamSCI, what is this? My passion for amateur radio really is what fueled my interest in academia and in grad school. And I wanted to see how we could join professional researchers who are studying the ionosphere with the amateur radio community. And I thought it was a natural fit because amateur radio really is built on this principle of experimentation and learning. And it's so directly affected by space weather and the environment around us. So I did start this when I was in grad school, and it's really taken off since then. We're now an official United States NASA citizen science project. I've been able to generate over $6.2 million in federal and private research funding since 2019 from the National Science Foundation, NASA, and ARDC. And our main objectives for HamSCI are to advance scientific research and understanding through amateur radio activities. We want to encourage the development of new technologies to support this research and provide educational opportunities for the amateur radio community and the general public. And so this really was first and foremost just a personal interest of mine. Here's my amateur radio station back from when I was in college. And now I'm located at the University of Scranton in Pennsylvania. You can see that here. We're about 5,600 kilometers or 3,500 miles from the Radio Society of Great Britain in Bedford in the UK. And this is where I live now. I've got my station in this little shack over here. And I use a ZS6 BKW as my primary transmit antenna. And here's my station. It's actually been upgraded just in the past couple weeks. I upgraded to an ICOM 7610, but it's a really cozy little spot for operating. And we're out in the woods, so it's a good spot for doing reception experiments and things like that. Now, at the university, I really wanted to bring the amateur radio experience to the university, too. So what is the University of Scranton? It's a Jesuit liberal arts university with about 5,000 students located in downtown Scranton, Pennsylvania. In my department, we offer undergraduate degrees in electrical, computer, mechanical engineering, physics, and more. I have some masters of software engineering graduate students running around as well. And up in the upper right photo here, you can see the brand new amateur radio station that we were able to install last year thanks to a very generous ARDC grant. And so now we have a beautiful HF station. We have a satellite station over here. We've got VHF, UHF over here. Skyhawk tri-band beam on the roof for 10, 15, 20. It's just beautiful. And we have this great view of the whole valley. So it's a really nice place for students to operate. Here's the outside of the building. There you can see our HF tower. We also have a fan dipole for 40 and 80. We've got a 70 centimeter repeater. We have omnidirectional antennas for 6, 440, 1.2 gigahertz. And we've got our satellite antennas over here. And right here is the club station. So it's a really nice place to introduce students and community members to the amateur radio, and also to be able to use this equipment for experiments. So as a little review, which many viewers are probably aware of, but we'll review it anyway, I'm very interested in the ionosphere because this is the region of the atmosphere that allows our HF signals to travel over the horizon and around the globe. And it's also very much affected by space weather. So the ionosphere is created by solar ultraviolet energy hitting the upper atmosphere and ionizing it, knocking electrons off of ions, and you get a plasma. During the day, when photoionization is occurring, the ionosphere typically breaks up into 4 different regions. The D is closest to Earth, then the E region, the F1 and the F2 region. And at night, when photoionization stops, some of these regions recombine, but the ionosphere doesn't go completely away. You still have an E and an F region. Of course, this is a very simplified cartoon, but it does illustrate some of the basic concepts that we're going to be working with. And with HamSCI, we don't just say, oh, how is ham radio or how is the ionosphere going to affect radio propagation? We often turn the question around and say, well, how can we use amateur radio to remote sense what's happening in the ionosphere? So this is another example of how radio waves travel through the ionosphere. This is what we call a ray trace diagram. I'm just going to pause it for a second here. And here you can see on 14 megahertz, we're sending a ray that's starting in Florida, and it's being received by a station in Wisconsin. And this is a model run that was done for August 21st, 2017, which is when we had the first Great American Solar Eclipse. So if I play this a little bit, you'll see that before the eclipse starts, the ionosphere is nice and strong. Florida is able to talk to Wisconsin. And then when the eclipse happens, the ionosphere becomes less ionized. The rays escape into space. They can no longer talk to each other. And then when the eclipse is over, the ionosphere builds up again, and they can once again communicate. And this is the path for 14 megahertz for these 2 particular stations. If you go up higher in frequency, the result's going to be somewhat similar. If you go lower in frequency, you may find that conditions actually improve during an eclipse because absorption may be less. So it's very interesting how radio propagation is so frequency dependent. So I first got into this HamSCI work for the 2017 eclipse, but in 2023 we had an annular eclipse over the United States, and in 2024 we had another total solar eclipse. So we created something called the Festivals of Eclipse Ionospheric Science. So here is, and I'm going to talk a lot about the results from that festival today. To kick things off, I'm going to play this one video from our local news station here in Scranton, W2NAF, Newswatch 16, where they did a story on our W3USR station on the day of the April 8th, 2024 total solar eclipse.
Students in Lackawanna County are learning more about radio waves and their connection to the atmosphere and to space.
It's part of a large research project at the University of Scranton. Newswatch 16's Emily Kress tells us more about how the eclipse can change how those waves work.
It's an all-day affair at the University of Scranton preparing for the total solar eclipse. While some students are just watching, others are working hard on research.
That's a lot of velocity change.
We're looking to see how this particular eclipse affects the ionosphere and the upper atmosphere. Every single eclipse is a little bit different, going through a different path.
Dr. Nathaniel Frissell is an associate professor of physics and engineering at the university. He says this research has been years in the making. Last fall, the university installed this tower to get a student ham radio station up and running at the Loyola Science Center. Students and other community members are able to connect with people across the country and the world.
When the eclipse comes through, it cuts off the sun and that photoionization, and so now the radio waves aren't bent the same way. And so when you receive the signals on the other end, or you don't receive the signals on the other end, if you look at things correctly, that can be attributed back to the eclipse.
Research like this is important because if we can understand how radio propagation works, we'd be better suited in cases like an emergency where, processes such as, phone lines or any other electronic communication wouldn't really work.
Students spent all day in the ham radio station since other parts of the world experienced the eclipse long before the eclipse reaches our area. The university was one of 5 chosen as part of a citizen science project with NASA. Through this research, students are helping to document history.
It's a pretty cool experience. It's like the environment and how everything is, all the people around here. It's very interesting to see it all play out.
It feels pretty great knowing that we're at the front of this, and would not have expected to have this great opportunity when I first came to the university.
Students will now spend their time breaking down all of the data collected. Emily Kress, Newswatch 16, Scranton.
That's what we're doing at W3USR on the day of the total solar eclipse, April 8th, 2024. So in 2017, when I first did the solar eclipse experiments, we had one HamSCI experiment. We called it the Solar Eclipse QSO Party, and that was essentially a contest-style operating event to create reverse beacon network spots that we could study after the eclipse was over. For 2023 and 2024, I had a number of collaborators working with me. I had more volunteers, and there were many different ideas on how we could study the eclipse and its effects on the ionosphere. And so we decided not to just do one experiment, but a number of them. And so we created the Festivals of Eclipse Ionospheric Science to cover all of these different experiments. So we came down with, I'd say, 5 major experiments. We had the Solar Eclipse QSO Party and the Gladstone Signal Spotting Challenge. We had the Personal Space Weather Station HF Doppler experiment and Whisper Demon observations. We had the HF Time Difference of Arrival experiment, the medium wave AM Doppler experiment, and the very low frequency experiments. And so we had different people in charge of each of these different events, bringing volunteers together and working to collect data and make all this happen. So I'm going to go over a few results from each of those experiments. So the first experiment was the Solar Eclipse QSO Party, and this is very similar to what we did in 2017. So again, this was a radio contest where we had hams communicate before, during, and after the solar eclipse. And then we were able to pull data from the reverse beacon network, the PSK reporter, WhisperNet, and participant submitted logs. And here's a summary plot of the April 8th, 2024 SCQP results. This is generated using PSK reporter, RBN, and WhisperNet results. What you're looking at here is 24 hours worth of data in these green plots. So from 0 to 24 UTC on April 8th, 2024. Every row is a different frequency. 28 megahertz is on top, 1.8 megahertz on the bottom. And the maps on the left show their heat maps of all of the spots that are in the plots on the right, which are the time series plots. These time series plots on the right also have a y-axis that goes from 0 to 10,000 meters, or 10,000 kilometers rather, and that shows you distance between transmitter and receiver. Over here in this big red box, I have where the solar eclipse occurred in time. And here you can see very well that on 1.8 megahertz, 3.5 megahertz, and 7 megahertz, there was a big propagation enhancement on all three of those bands. And we believe that is because when the eclipse, the shadow of the moon, came across the operating region, the D region of the ionosphere started recombining and you had less D region absorption. So that allowed more signals to go through. Additionally, the upper layers of the atmosphere might become less ionized, so it allows for longer refraction. In these higher bands, it's harder to see the effect quite as well. But I'm going to show you some plots where our postdoc, Dr. Kuldeep Pandey at New Jersey Institute of Technology, is starting to dig into this data a little bit more. So these plots come from Kuldeep over at NJIT. And so here's some 7 megahertz data. This is very similar to the time series plots I was showing you before, but now we have it broken up into continental United States stations on the left and global stations on the right. And then we have it, instead of organized by universal time, we have it organized by hours relative to eclipse maximum. So right in the center is where the eclipse maximum is at 0 hours. And then along the y-axis, it again goes from 0 to 10,000 kilometers. And on the x-axis, it goes from 2 hours before the eclipse to 2 hours after the eclipse. Here on 7 megahertz, you can see that the continental United States stations definitely saw an increase in range of 7 megahertz, which is similar to what you'd see at night on 7 megahertz. The band goes long. If you look at the global data, all of the data, you again see the enhancement of propagation between, say, 2,000 and 2,500 kilometers, but also in what we think is the second hop or multi-hop propagation, farther distances, you see an enhancement here and also an enhancement there at 7 megahertz. So now we can see that farther ranges as well. Here's some 21 megahertz data. So this again is organized in hours relative to the eclipse. So here's the local data and here's the global data. And with the 21 megahertz data, the effect is not quite so obvious, particularly at close-in ranges. When you get out to these farther ranges, between 4,000 to 8,000 kilometers in distance, you can definitely see a drop-off in the amount of propagation. Kuldeep also made plots where he looked at continually operated transmit-receive pairs. So he identified stations that were pairs of transmitters and receivers that were operating continuously between the hours of 14 UTC and 22 UTC, and he worked just with that data. He also made plots of the day of the eclipse, which is on the left-hand side, with 21 megahertz on top and 7 megahertz on the bottom, and the day after the eclipse, so no eclipse on April 9th, as a control day. And one of the really interesting things that came out of this analysis is you can see over here on 21 megahertz, and you can see this drop-off at around after 1930 UTC in the longer ranges, 6,000 kilometers. This is not during the eclipse interval, and yet that same drop-off does not appear in the control day. So that is a very interesting feature that we have not before appreciated. And so why might that be? What he's looking into is it due to the extended shadow-like conditions? So on that particular day, on the eclipse day, when you get towards the end of the eclipse shadow seemed to join in with the terminator right over the UK, actually. And so that might be the cause of those extended condition changes. Another thing we're doing is we have my collaborator, Dr. Joseph Huba. He runs an ionospheric model called SAMI-3. And this is a first principles physics model of the ionosphere. And this is showing us, so we're able to use physics equations to predict what the ionosphere should look like. And then we can compare that with the data. So this is a model run of the April 8th eclipse. And over here, Kuldeep is comparing the data, which is in this left column over here. Again, we have the epoch analysis on top. We have the continuous stations on the bottom. So this is organized. The epoch analysis is organized around hours relative to maximum eclipse. The bottom plots are organized relative to UTC time. And then in the plots on the right-hand side, this is all generated using ray tracing, like I showed you before, and the SAMI3 model. And Kuldeep has the model split up into two different layers. One is the refraction point of the radio rays is below 125 kilometers, so we say like E region refraction, or it's above 125 kilometers, say F region refraction. And then what you can do is you can look at the plot on the left, the actual data, and you can see how well that compares with the model. And here, you tend to get much better agreement between the data and the greater than 125 kilometer modeling, which suggests that most of the signals were refracting off of the F region during this particular event. And so there's 7 megahertz. Here's 7 megahertz again, but we're using a different neutral atmosphere. So with these physics-based models, you have to specify which neutral atmosphere and which initial conditions you're going to use. And we have a few different ways of doing that. So we're working on that. Here is a comparison of the 21 megahertz data and SAMI3. So this one, you can see there are quite a few differences between the model and the data. So there's definitely some things to look at there. And that's about where we are right now. So Kuldeep has been working on this data just for about a little bit less than a year so far. So we're working on trying to get this to a state where we can publish some results on that. So that's the Solar Eclipse QSO Party. Another experiment that we have is a personal space weather station, the Grape HF Doppler experiment. And so the idea here is that if you have some sort of a beacon like WWV, which is located in Colorado and is run by the U.S. National Institute of Standards and Technology, it's transmitting a known signal on 2.5, 5, 10, 15, 20, and sometimes 25 megahertz. And it uses atomic clocks to stabilize its oscillators. So it provides a very precise frequency reference. On the other side, you can have a receiver that if you use a GPS disciplined oscillator, you can also take very precise frequency measurements. And if you listen to the CW carrier from WWV with one of these GPS DO locked receivers, you'll find that the signal is not exactly at the carrier the entire time. It will frequently deviate by, say, plus or minus up to about 5 hertz. And one reason for that is the path length of the radio propagation can be changing with time as the ionosphere varies. So one possibility is that the path length increases. That makes the path length is longer, so then you get a decrease in received frequency. If the path length gets shorter, goes the other way, you get an increase in frequency, or a positive Doppler shift. So this is the HF Doppler shift idea. And we currently have 3 different devices that we're using to measure these Doppler shifts. This started with the Case Western team led by John Gibbons, NAOBJ. And since about 2019, they've had these devices. That little purple board there is called a Grape 1 receiver, and you can actually build that yourself. And what you do is you just put in an HF antenna here, and you mix it with a signal from a Leo Bodner GPS discipline oscillator, and then that outputs an audio signal that you can feed into a Raspberry Pi, and you can measure these Doppler shifts. Then we came up with the Grape 2, which can do 3 bands simultaneously, and this we deployed about 30 of these for the total solar eclipse. And then now we have this Whisper Demon Grape system, which Gwyn has been very involved with. And this development is being led by Rob Robinette, AI6VN, and Bill Karn, K9Q, does the K9Q radio software. This RX888 radio can digitize the entire HF band simultaneously, and you can decode an arbitrary number of slice receivers in a modest CPU using the K9Q radio software. So this is really what we're deploying today. So what does data from this system look like? If you have an original Grape 1, you might be recording only a single frequency as a function of time. And so here are observations from all across New England. Every single one is a different station in New England listening to 10 megahertz WWV. And you can see this is the night over here. Then right over here, you get this big hump. That is dawn. So the ionosphere builds up, comes closer to the ground. You get a positive Doppler shift. And then over here, you have the effect of the annular eclipse. And that's like temporary night. So night comes on, you get negative Doppler shift. The eclipse ends, that's like dawn, you get a positive Doppler shift, and then things go on. You can see there's one station that's not in step with the others here. That's the purple one, and that's because that's actually not in New England. It's actually in British Columbia. So you can see differences based on where these stations are located. Now, so we deployed, this is what our deployment map looked like for the April 23rd eclipse. We got more stations out for the April 2024 eclipse. And I'm now going to show you some results from the instruments I had at my station here, W2NAF, and you can see my relationship to CHU. You can also see my relationship to WWV over here. And one of the things we found, I've learned by working with people in this project, is that really looking at a single frequency as a function of time is not adequate for understanding what's going on with the received signal, with the Doppler shift, and with the radio propagation. Really what you need is a spectrum. And so that's what these Grape 1 digital RFs and the Grape 2s and the Whisper Demon grapes are able to capture a spectrum of data. So here's 24 hours worth of observations from the annular eclipse on October 14th, 2023. And again, you can see dawn here. You can see the eclipse curve right here where it goes down and then up. That's a constant S curve. But now in addition to just seeing a single line wiggle, you can see all sorts of different traces. So there's evidence of multi-path propagation, you know, things going off the, maybe off the E layer and simultaneously off the F layer. And maybe you have one hop and two hops F happening simultaneously. You have many different modes. And Gwyn will probably talk about that a bit more in his portion of the presentation. But with this spectrum view of the HF Doppler shift, it's a much more rich data set to look at. Here's from the April 8th total solar eclipse at my house on 5 megahertz, 10 megahertz, 15, and 20 megahertz. You can see how the signals change as a function of frequency and as a function of time. So through the night, the 5, 10, and 15, 5 and 10 megahertz are definitely the strongest. And during the day, 15 and 20 megahertz are stronger. You can also see, the eclipse very clearly here and here, a little bit down there, a little bit up there. You can also see these beautiful oscillations, these traveling ionospheric disturbances moving through the night. So that is where I think I'm listening to WWV. But there actually is, you know, WWV is not the only station on these frequencies. WWVH is as well. So that is a bit of work we have to do to disambiguate that, and that's something that we are working on. Gwyn will also say a few words about that. Here are some observations from CHU. These are all taken with the Whisper Demon Grape system. So that one system is able to record all of these frequencies simultaneously, the Grape mode, while at the same time that the Whisper Demon system is doing this, it's also decoding all of the whisper spots on all of the HF amateur bands. So it's a very, very powerful system. Another experiment from the Festivals of Eclipse Ionospheric Science was the high frequency time difference of arrival experiment. And this was the brainchild of one of our volunteers, Steve Serwin, WA5 FRF. And he came up with this idea. He said, you know what, we can go build our own hardware, but it'd be really neat if we could do some ionospheric measurements just using commercial off-the-shelf amateur radios that are not disciplined by GPS DOs and are unmodified, and you just get your 3 kilohertz of audio bandwidth for a standard single sideband channel. And what he figured out is that if you send some sort of a linear audio chirp through the passband, you can have a situation where if you have multipath, you might get, the 1 hop and the 2 hop all received at the same location at the same time. But they will be, one copy of the signal will be delayed a little bit relative to the other. And so you can see here's a simulation of that, where if you take this 100 hertz per millisecond chirp and you delay a copy of it and change the amplitude by 3 dB lower, you delay it by 1 millisecond, the receiver, if it's getting this on multipath, will sum these up and you'll get this beat note that rides on top of the carrier. And you can measure that beat note. So here it's 10 milliseconds. And you can actually use that and the simple geometric model to back out the height of the ionosphere. So this works only if you have multipath going on between the stations. But we did apply this. We ran that experiment for both eclipses, and we especially focused on stations near Steve's house. He was very lucky. He was located right at the nexus of both eclipses, and he talked to a few of his friends, and every 10 minutes they would send one of these chirps, and my student Alex Papadopoulos and them, they would record the chirps that were received, and then they could run their algorithm on it and figure out height changes. So these are results from the 14 October annular eclipse, one of the 7.2 megahertz runs. And the colorful dots are the measurements made by the thick black line, which is the blue, the orange, and the green colorful dots. Those are all measurements made with that amateur radio technique. And you can see it's putting the height of the refractive layer, the refraction height, at around 262 kilometers high. That agrees very well with the purple dots and the pink line, which is the Austin Ionosonde, which is a professional grade instrument. So it's really neat to see how much agreement is there. And then this is April 8th, 2024 results done by Steve. Also very good agreement with the Austin Ionosonde. This is on 5.3 megahertz. So it's neat to see how well this very simple technique can agree with the Ionosonde. We also had a volunteer up in Canada, Nicholas Hall Patch, who is interested in medium wave AM broadcast experiments. And actually, for the 1999 eclipse in the UK, Dr. Ruth Bamford at the Rutherford Appleton laboratory, she coordinated a big ionospheric eclipse experiment, and she included quite a few results from AM broadcast in there as well. So we looked at her work, helped to inspire some of this. But in this experiment, we used regular AM broadcast radio in the medium wave band from 530 to 1700 kilohertz. And so, at night, medium wave AM can propagate hundreds of thousands of miles via E and F region refraction when the D region absorption is reduced, and therefore you can see eclipse effects. And so here, if you're interested in the Ruth Bamford report, you can get that over here. So our volunteer, Nick Hall Patch, VE7DXR, he coordinated a similar medium wave AM experiment for the 2023 and 2024 eclipses. And he got, well over 25 terabytes of data from almost 40 participants throughout the world. And that data, much of it is available on Zenodo now, so you can go play around with it. Here's some of what you can see. So here's an example where AM broadcasters were heard in Arkansas from Texas and Ohio in the daytime. So normally there would not be any distant AM broadcast signals heard in Arkansas during the daytime. However, on 1530 kilohertz. The April 8th eclipse progressed. Broadcast signal faded in from Texas and in and out, while another broadcaster came in from Ohio. It looks like I'm missing a couple of figures here, but I can possibly send those results on later. There were some very nice, Nick had some very nice figures showing that. We also have another one of our volunteers, Jonathan Rizzo, KC3EEY. He is very interested in very low frequency. And so he developed this receiver, which we installed in my backyard. And this is for receiving very low frequencies for the purpose of capturing natural radio emissions, sudden ionospheric disturbances, and VLF transmitters and VLF amateur radio transmissions. And here's an example from the eclipse. So in this particular, this is data that was all captured with this system from the eclipse day. We're actually not listening to natural radio emissions here. We're listening to US naval VLF transmitters, but you can see over here, there's a nice increase in the signal strength observed with the eclipses. All right, all of these systems, the VLF system, the Whisper Demon system, they're all part of this personal space weather station project that we not only used for the eclipse, but we're also expanding and building out that network now throughout the United States. And there are some receivers in the UK as well. And why don't we hear from Gwyn, G3ZIL, who can talk a little bit about his experiences with HamSCI and some of the observations he and his friends have made. Gwyn, go ahead.
Thank you, Nathaniel. It's my great pleasure, really, to join Nathaniel tonight and give a perspective from the UK, from a citizen science as regards the ionosphere. First of all, I learned a lot from the HamSCI Google group. So I find it really an effective forum for HamSCI exchanges. For instance, I reported what may have been, I thought it might have been, a solar radio burst seen in the graphs in the center on 12 and 10 meters at stations in the western United States in December 2023. Confirmation came from the research community in this response on the HamSCI Google group from Dr. Phil Erickson, W1PJE. He'd bothered to go get some data from Dr. Alan Rogers, his distinguished colleague at the MIT Haystack Observatory. So these small peaks in noise seen on the amateur systems were indeed from a spectacular radio burst, seen in the graph bottom right by Dr. Rogers, where the y-axis is frequency from 40 to 130 megahertz, and the color is noise temperature, the noise level. Now, as a lone amateur, without HamSCI, I'd have had little chance of getting immediate confirmation from a trusted professional source. Next slide, Nathaniel. Another aspect of HamSCI I enjoy is collaborative work on computer models that help scientists and amateurs better understand the ionosphere. So the PyLab ray tracing package is a good example. So it was originally developed as PhyrLab by Dr. Severa and colleagues at the Defence Science and Technology Group in Australia. It uses MATLAB, which has hefty license fees. Now Nathaniel and Bill Lyles, NQ6Z, a HamSCI advisory board member and RSGB Propagation Studies Committee associate member, came up with the idea of a Python front end for PhyrLab. Development was taken on by successive undergraduate and master's students, supervised by Nathaniel and Bill, and Devin Deal, a University of Scranton software engineering master's student, taught me how to use PyLab. And then, in return, my own work gave him a novel use case, exploring two-hop side-scattered propagation. And we roped in two amateurs to make whisper measurements with a rotating beam, and we presented novel results comparing the model and measurements in a poster at the 2024 HamSCI workshop. Next slide, please. Now, I've learned much on HF propagation and even some ionospheric physics from HamSCI's Thursday online science meetings. One gets to know the particular interests of researchers, and sometimes how one's own knowledge as an amateur might be of assistance in their studies. For example, while there's no way I can contribute to Kuldeep Pandey's work on computer modelling that Nathaniel has shared with you this evening, I can search the WHISPER database. I knew, for example, that Mike, G3ZIL, was both one of the closest UK stations to North America and one of the UK top WHISPER spotters. And so here's the best example I could find for Kuldeep on the transatlantic path on 7 MHz for the 8th of April 2024 eclipse. As the eclipse came and went, the signal from Bernard, VA2CY, near Quebec, rose in SNR, reached a maximum, then fell. So here's a nice example of reduced absorption in the D region during the eclipse, reading to a higher than normal SNR. And what those careful measurements by Mike in Cornwall bring is a quantitative dB scale to that reduced absorption. Next slide. There is one HamSCI Whisper Demon Grape RX888 receiver operating in the UK currently, thanks to Nigel, G4HZX, South London. So Nigel has a simple trap vertical antenna at the end of an admittedly long, narrow garden, and Nigel captured these wonderful Doppler spectra on the left from station CHU, Ottawa, Canada, during the eclipse this year, the 29th of March partial eclipse. Now, what was a real surprise to me was the spectrogram on the right. So we've seen eclipse-induced Doppler here on 15 MHz from WWV Hawaii, an 11,000 kilometre path to Beckenham, South London. And here's a great example of why HamSCI isn't just about the USA. We would only have seen this on a path from WWVH to Europe. Next slide. The Doppler trace from WWVH to G4HZX is indeed my current project. Now at the top, PyLab again, after Devin's tutoring, suggests the signal propagated via caudal hop on its way north, with no ground reflection between the first two ionospheric reflections. But the caudal hop was outside the eclipse zone. However, reflections 3 and 4 were likely affected. And in the bottom trace, the negative Doppler shift indicates, in part, as Nathaniel has shown us, a rising height of reflection. But unfortunately, the path closed at G4HZX just before maximum obscuration. But it still leaves me with a negative half cycle and several curiosities. Why is the slope B, which is after maximum negative Doppler, greater than slope A beforehand? And I've no doubt that in the months ahead, conversations with my many HamSCI friends will provide clues and perhaps answers. Thank you. Back to you, Nathaniel.
Thank you so much, Gwyn. I really appreciate it. So the question is, what's next for HamSCI? So for one thing, we're going to continue the science analysis using the existing HamSCI data sets and instrumentation. And we have so much out there. As you can see, we're really pouring through the eclipse data right now. We've been collecting personal space weather station data so far. We now have the WhisperNet, reverse beacon network, and PSK reporter data archived onto a Madrigal database run by MIT Haystack. And the Whisper Demon group, they're running their own database as well. So there's so much to look at. We want to continue our build out of the personal space weather station network. We're looking to deploy some personal space weather station compatible receivers to Antarctica, to the US Antarctica stations. We're looking now to have a meteor scatter QSO party, which is going to happen this coming August and December, when some of the meteor showers will be coming. And for this to participate, all you need to have is either a 10 meter or 6 meter or radio, and you want to be able to use it with WSJT software in the MFSK 144 mode, and then you can participate. So this might be something that you'd really enjoy participating, and you can learn more about that on our website, hamsci.org/MSQP. And the meteor showers we're going to be working on are August 11th and 12th of this year and December 12th and 13th. And if you'd like to get involved, please go to our website. You can hit the blue Join HamSCI button, and there will be a link to get to our Google group, which now has over 1,300 members. We also have a number of specialized email lists, and we have weekly telecons. So if you'd like to participate with us in real time, we have 3 public telecons every week. One is tonight at 9 p.m. Eastern, which is 1 UTC. That's every Monday night. That's the Tapper HamSCI technical session. So that's when we have an engineering discussion about the design of new instrumentation. We have our PSWS technical or operations telecon. That's on Thursdays at 10 a.m. Eastern, and that's where we discuss the support operations of the HamSCI personal space weather station. And finally, we have the Ham Science Telecom on Thursday afternoons at 4 p.m. Eastern, which is 20 UTC. And this is a science seminar series and general telecon to support HamSCI's mission. So please come join us. We're doing some very unique advanced space physics and research right here in Scranton. Not just right here in Scranton, but also throughout the globe. And that's where many of our collaborators are. So please come join us. And I'm especially grateful to all of the National Science Foundation grants, NASA grants, and ARDC grants that we've gotten, and especially to the amateur radio community volunteers who've contributed to the HamSCI projects like Gwyn. And these are some links that Gwyn would like you to have, including a link to PyLab and some of his presentations in the Whisper Demon website. And you can also find out more just by going to hamsci.org. So thank you very much.
Thank you very much, Nathaniel. Well, and as they say, I never believed there was so much to it. It's amazing, isn't it? I mean, I think most of us in this hobby realize how diverse it is and how many things you can do. But the stuff that you're doing in this, and it's not just for our hobby, is it? It's going to benefit other scientists doing other science, shall we say, real science in the real world, as well as benefiting our hobby. So it really is important. So thank you both very much for your presentation. Of course, if you're watching this tonight live on the 12th of May, then this is a great time to ask questions or make comments on either YouTube or BATC. Please put your name and your call sign in every message if you can. So we look forward to getting some of those messages. I think the first thing I'd like to do, I know you have just explained how people can join, Nathaniel, but it seems to me that it's not just joining something to find out things. You can actually play a very interactive part. So could we just zone in on that for now? What an amateur, most I guess watching this will be in the UK, but wherever you're watching this, what they can do and how they can contribute and interact with the project?
Well, I think it really depends on a person's particular skill sets and interests, David. And a really good way to start out is to join one of our telecons and just meet some of the people, or join our Google group and see what's going on. And, you know, the way you can participate ranges vastly. So someone who is really more of an operator and doesn't necessarily understand so much of the science behind it, or doesn't necessarily understand so much engineering, they might be able to do something like participate in the Meteor Scatter QSO Party, where you can just use your regular HF or VHF radio and WSJT, and you're operating it very similarly to the way you would operate FT8 or FT4. And so that's one end of things. Another end of things might be doing data analysis. You can join our Thursday afternoon group, and maybe you have skills analyzing, visualizing data, or being able to read research papers, or be able to help dig into our data sets. And that's one of Gwyn's real talents. He calls himself an amateur, but he really has a lifetime of experience as a professional oceanographer in the academic world. So he's able to bring all of his research skills from that over to what we're doing here, and it's absolutely invaluable. We also have people who are RF engineers, and they join in our Tapper telecons, and we're trying to develop new hardware. So people who are actually good at designing hardware, they might join that particular group. Some people really aren't very technical, and they like helping out with a website or with marketing. So we have some people who are doing more of those sorts of activities on the communication side. So really there's kind of something for everyone who wants to be involved. So the best thing to do is to just jump into some of these telecons, or email HamSCI at hamsci.org and tell us what your interests are, and we can help you to find a niche.
Yeah, that's wonderful. I'm just reading actually a quick message that's been sent to me by Steve Thomas, who's M1ACB, who's the RSGB General Manager, and he'd like me to say a special thanks to both you and Gwyn for a fantastic presentation tonight. And also he adds to that, Nathaniel, that he looks forward to meeting you again in Dayton later this week, so you'll see him.
Thank you. I'm really looking forward to that as well.
And I think I'll add now, and I would think I was the first to congratulate you, but I think he'll be very pleased, and many people watching as well will be pleased to hear that you joined the RSGB just minutes before we met this evening, about 20 minutes before we started the broadcast. So thank you very much for joining us as well.
Oh, you're welcome. I've been thinking about it for a while, and I finally did it.
That's excellent. Thank you. Okay, so I mean, there was something else you mentioned. We haven't really got any questions or comments or anything yet, really, which is, I mean, everybody's saying how wonderful it all is. G6AD says amazing to see HF propagation rather than just hear it. And of course, this is one of the things, isn't it? It does help to visualize this, all of the graphics, and make it very real. There was a mention in a slide a few minutes ago, and I'd like to find out a little bit more about it if I can, about the HamSCI Personal Space Weather Station. Can you tell us a bit more about that?
Sure. I think it might be useful pointing people to our website too.
Yeah, sorry, I put you on the spot, but it's it is something that I think a lot of people would be very interested in.
Can you see the website there?
I think we can. Yeah, we're now going to put it up. Yes, here we are.
If you go to hamsci.org, you can click on HamSCI Personal Space Weather Station right there. And the goal of this is to create a multi-instrument system, ground-based system that's capable of receiving or of detecting space weather essentially where you are, and then also reporting that to a larger area, to a global data set. So we actually have three main components of it's a little more complicated on the website, but there's really three main components of a personal space weather station. There's an HF receiver, there is a VLF receiver, and there is a ground magnetometer. So in this particular page, you see 4 different versions of the HF receiver. And we've gone through multiple iterations, and all of these are still out there in the wild and running different things. But if you are a person who's new to this project and you're like, what's the one way for me to get involved in this project? I would recommend clicking on this Whisper Demon grape receiver system. If you click on this, you get to this page where it tells you what it is and how to build one and where you get the parts. And really what this is it is a full software-defined radio receiver that can receive up to about 60 megahertz, and it can digitize that entire band, and it sends it over a high-speed USB port to a rather modest, AMD Ryzen 5 or AMD Ryzen 7 computer, and then it can be used to make all of these Doppler graphs that I've been showing, and it can also simultaneously be used to decode all of the whisper signals. And at the same time, it has a web-based interface, so you can use it as a regular web-based software-defined radio receiver. So even if you don't know a whole lot about the science, if you want to play with a nice new SDR shortwave HF receiver, you can get one of these. You can actually listen to it through the web-based interface, very similar to a Kiwi SDR. But at the same time, it can run this Whisper Daemon software and do all this scientific reporting.
That's excellent. Well, thank you for showing us. I know you did show briefly this earlier on, but it's really good to actually see it there. So more details for you at home. HamSCI.org is where you need to head to find out more of this. Gwyn, you got involved with this project. Clearly, being a member of the Propagation Studies Committee, you are already very much involved with this sort of science. But I believe that you had a particularly good experience, and this has been really useful for you to join. So can you tell us a little bit more about your experience with it, Gwyn?
Well, it really started for me again in true radio amateur fashion. You come across somebody that need not be in your club locally or even in your own country, but Glenn Elmore, N6GN in Colorado. We started to converse about noise level reduction and so on, and we wanted to measure noise levels. And we started to do that, and then he brought in another friend of his, Rob Robinet, AI6BN, who sort of said, well, we can do this systematically with Kiwi SDRs, that it was the time, before the Whisper Daemon Grape. And I started work with Rob to put it into a database. And then Rob said, well, I've come across this organization called HamSCI. I'm sure they'd be interested. And it sort of grew like Topsy. So that was sort of my personal introduction to it, really. And as Nathaniel said, it fitted in well with some generic data processing skills that I had. But let me also give you a UK example. The National HamFest, I was manning the stand with for the Propagation Studies Committee at the National HamFest in Newark last year, and talking about the work of HamSCI with a poster. And Jerry Bulger, G3WIP walked by, and we got talking, as one does. And he got so engrossed by what you could do with the Whisper Daemon Grape that he's a peripatetic retired doctor who goes to out-of-the-way places. This week, he's landed in the Falkland Islands. So he's now reporting from one of these stations, Whisper Daemon station there, as VP8 DPD. So not only that, he then bought a separate system to install on St. Helena. And that started reporting this week as Zulu Delta 7 GB. So, we have sort of a domino effect here of amateurs learning about HamSCI, becoming engaged, going out, investing in their own equipment, and really putting stations into interesting and out-of-the-way places.
Indeed. Yes, thanks very much, Gwyn. It's been good. And I mean, I know you are very deeply involved with the subject as well, but I think we should stress that this isn't just for real experts in this sort of thing. This is ideal for curious amateurs, for something else, something a bit different to do, but also something where you're going to contribute not just to our own hobby, but also maybe to the greater science, the greater world of science really in this. So it is wonderful.
Well, perhaps on that, if I may interrupt, David.
Yeah, of course.
Nathaniel was the lead author on, first of all, a white paper, as it's termed in the science community, looking forward for a decadal survey for the US National Academies of Science to contribute to the areas of heliophysics. So I think we can see Nathaniel has it on his screen. So heliophysics and amateur radio. So in the very title of a white paper, and then in the title of a freely available journal paper, there is heliophysics and amateur radio. It's central to the next 10 years of the research agenda. There are still questions that we as radio amateurs can contribute alongside our friends in the academic community.
Yeah, absolutely. In fact, it might be a good time to mention and to say congratulations again to Nathaniel, because he received the Les Barkley Memorial Award just a month or so ago in the RSGB AGM Awards. So well done for that, Nathaniel.
Thank you.
It was really good. In fact, you can find out more details about that award and other things in the May edition of Radcom as well. I think that is getting there now. We've got a comment from Martin G3ZIL from the Cambridge area. Is saying just a comment that he is promoting this to some of the students at Cambridge University. So I hope that one or two of them will also get involved. They've got a very active wireless society, the Cambridge Wireless Society, and maybe one of the meteor shower days from our club station as well. So all good stuff. This is just the start, I'm sure. Thank you both very much indeed for joining us tonight. And it's been a wonderful presentation. And as you know at home, where to go for more information, it's hamsci.org, as we've been putting on, I think, most of the slides earlier. And Nathaniel's email address is nathaniel.frissell@scranton.edu. Once again, to both of you, thank you very much indeed.
Thank you.
Thank you.
Thank you. Thanks to Nathaniel and Gwyn, and of course thanks also to the team who helped put this series together behind the scenes, and thank you for joining us. We hope you've enjoyed this tonight at 8. Why not click the thumbs up on YouTube if you did? We hope you'll be able to join us next time. We'll be looking at all things Morse code with Eric Artenstall, M0KZB and colleagues. Well, if you'd like to see details of future webinars or watch recordings of previous programmes in this series, please visit us at rsgb.org/webinars, where you can also send us comments and feedback. And if you subscribe to the RSGB's YouTube channel, you'll be notified of all upcoming Tonight at 8 webinars, as well as other new videos and presentations from the Society on a wide range of amateur radio topics. Thanks for joining us this evening, and until next time, this is David G7URP signing off and clear. Bye-bye.